as beneficial as one might think. You do have a lot of electrons in that these lower energy orbitals, but you did have to pair some of them. So you had one, and if two of them are paired, you can see sometimes 2 PE. So some books will do that, some books will not. So I just wanted to mention that both are okay. And whether you're asked to write that or not, and the question will say include the pairing energy, so you know whether you're supposed to do that or not, that there is that energy associated with pairing in this strong field case. So, great. Okay, so let's look at another example. And then you should be all set to do these problems for an octahedral field. So we'll take our electrons down. All right, so let's look at a case of cobalt +2. So let's consider how many we're going to put in. The oxidation number is +2. And what is the D count then? What group number? 9 minus 2 is 7. So we're doing a D7 system. All right, so now for the weak field case here, why don't you tell me what is the correct electron distribution? Okay, let's just take 10 more seconds. Okay, very good. So this is the weak field case. So in this case, we are going to fill up singly all of the orbitals because the splitting energy is less than the pairing energy. So we're going to put them to the fullest extent possible before we have to pair. So we have 7. So we're going to do 1, 2, 3, 4, 5. And now we have to pair. We've used up all our orbitals. So we're going to start pairing down here in the lower energy. So that would be 6, 7. So we had no choice. We had to pair them. But because it was a weak field, we filled them all up singly first before we paired. So now let's consider what we're going to do down here. Now remember, this is a strong field, so there's a big splitting energy. So it takes less energy to pair them than to reach this higher level. So first we put them in the same way, 1, 2, 3. But now that we have the 3 in, it's better to pair than to bring them up here. So we'll do 1, 2, 3. We'll pair them all up. Now it's all filled. We have no other choice but to go up here. So we have these very different cases depending on the splitting energy. So what controls the splitting energy? Well, what controls the splitting energy is the nature of the ligands. So we're going to be talking about that next time, and you'll recognize for certain kinds of ligands you're going to have a strong field, and other kinds you'll have a weak field. But right now we're not talking about that. We're just showing those two possibilities. So for this system, is this going to be a high spin or a low spin system? So this will be high spin because we have the maximum amount of unpaired electrons. And over here, we're going to have a low spin system. We have the minimum number possible of the unpaired electrons. All right, so let's finish this up now and do our dn electron configurations and our crystal field splitting energies. So for this case, we're going to have in our T2G system how many? 5. And in EG, 2. And for our splitting energy, we have 5 times minus 2/5 times the octahedral crystal field splitting energy plus 2 times plus 3/5. And what does that end up equaling? Minus 4/5 times the octahedral crystal field splitting energy. And we could also optionally put 2PE because we have 2 sets paired. All right, so let's look at our strong field system. How many do we have in our E2G set? 6. What about EG? 1. And for our splitting energy, then we have 6 times minus 2/5 times the octahedral crystal field splitting energy plus 1 times 3/5. And what is that going to equal? Minus what? 9/5. And how many pairing energies? 3 pairing energies. Great.